Hi, everybody. Welcome. Thank you for joining us today. My name is Jennifer McConnell, and I'm the product manager for the in-situ systems here at Protochips. And we're really pleased to welcome you to the next installment in the AXON product webinar series, AXON Unleashed, delivering on the promise of atomic scale dynamics in the TEM. Now, again, we really appreciate you joining us today, and we hope that you and your families are weathering the current global crisis as safely as you possibly can. We will have a question and answer session following the presentation, and we'll try to get as many of your questions answered as we can. But please do enter your questions into the chat box on your screen. If we don't have time to answer them today, we'll reach out to you separately after the webinar to make sure we get you the answers that you're looking for. So without further ado, why don't we go ahead and get started? The new Protochips AXON system started shipping to customers at the end of March of this year. And although we were off to a really great start, the global pandemic has delayed many customer efforts to have this exciting new product installed in their labs. And if not for this interruption, we feel sure that the facilities around the world would have already been generating and publishing data at new levels of performance enabled by AXON. And then if that were the case, this webinar might not even have been necessary. So even though the labs are starting to reopen and the AXON system is shipping for use on both Thermo Fisher Scientific and JUL columns, we didn't want you to wait any longer to begin to see the actual performance improvements that AXON brings to these microscopes. So we decided to generate some of that first data ourselves to share with you today. So in this webinar, we will attempt to bring you several new aspects of the AXON system. We'll briefly review the design concept and goals for the AXON product and how it's meant to change your work. And we've received actually a lot of questions from customers on how the drift correction aspects of AXON compare to those already found on many TEMs. So we'll go over that today as well. And as I mentioned a moment ago, we use the AXON system to run an actual experiment in one of our facilities. And we're going to show you the difference it made when compared to the same experiment prior to AXON. We'll explore some of the tools and features you'll use in AXON that will greatly improve your productivity. And of course, we'll select one of you attendees to receive a new AXON system for your laboratory. It'll be fully installed and free of charge, the best part. In order to qualify, you're going to have to meet a few different criteria. So you'll need to attend this entire webinar starting now and remaining until the end of the session. Answer any of the polling questions that may be presented to you in this webinar. Complete the survey that will appear for you at the end. It'll pop up as the webinar ends, and have a compatible TEM and imaging system currently installed and available to enhance with AXON. Okay. So some of our target goals in designing the AXON machine vision platform include making the operation of a TEM easier and simpler for all users despite experience level, especially when they attempt more challenging in situ experimentation. Minimizing those portions of your experiment that demand so much effort on repetitive TEM tasks, and they tend to steal your attention away from the work you're actually trying to do. We want to free you from drift, allowing you to perform your experiment at magnifications far higher than before, and you'll generate much higher quality data as well. Automatically and continuously align important experiment parameters from your microscope, your imaging detector, and your Protochips in situ systems, all in the background. And so AXON will even control the Protochips in situ system for you. And since AXON stabilizes the portions of the experiment in which instability previously prohibited the collection of high-resolution data, AXON customers should suddenly have access to new and potentially exciting phenomena, even under aggressive in situ conditions. So I mentioned running an in situ experiment typically demands a high level of expertise in the operation of the microscope. Now, that's not always an available resource to scientists interested in exploring dynamic studies. And the global pandemic that we're in has also changed a lot of the rules in many facilities, in that only one person at a time is allowed at the TEM lab. So the workflow improvement delivered by AXON not only makes this work more available to even a novice user, And many times it allows the in-situ researcher to run the experiment without a TEM operator present for a majority of the time, actually. Now, especially in the presence of drift caused by heating or other stimuli found in many experiments, the intense requirement of constantly chasing and recentering and refocusing your region of interest can dominate the session, and it really will distract you from the experiment at hand. So AXON removes the actual source of this misbehavior. It removes the drift itself, so you can keep your full attention on the science. You'll watch your sample through the entirety of the experiment, even while you're altering the conditions, because AXON is handling all the distractions for you. Now, being trapped at lower magnifications while applying even much reduced levels of stimuli can drag out your experiment, and that can be incredibly frustrating. Now, since AXON has addressed the drift, you'll be free to get in close and see what's really happening in your sample. Take advantage of the magnification that gives you the sample area you are interested in, and it fills the full field of view, and you'll have confidence that you won't lose that area through the course of your work. Now, for most in-situ TEM researchers, the real work begins at the completion of image collection. Now you'll have the daunting task of trying to gather, align, and assemble all the parameter information from several different pieces of equipment. And then you have to accurately lay them over the experiment timeline. This can take a very long time. And the result, you may result in only a few pieces of actually usable data applied with a limited amount of accuracy. And since AXON now automatically marries all of the metadata in your experimental systems to each image, you are ready immediately to analyze and publish your work. And since there's so much more data there, you'll find rich new ways to use it to tell your story. So let's take a moment to answer that common question I said so many customers were asking. The question being, how is AXON drift correction, how does it compare to that in my new digital TEM camera? And so the phrase TEM drift correction actually is a little bit of a misnomer. The camera systems with this feature are not actually correcting the sample drift. They're actually manipulating the digital image data to address specific artifacts that are generated in the image due to the presence of drift. So a better name for this function might actually be digital image correlation. So we're all very familiar with the problems induced in your work when the sample drifts. Collecting a sharp, coherent image as your sample moves is frustrating and ultimately limits the best quality or resolution from being recorded. As the sample drifts, the images are misaligned and combine to form something that's blurred or a really confused looking image. Now, depending on the amount of drift and the size of your field of view, you may not be able to record your intended region of interest before the sample moves out of the frame. This may force you to work at magnifications lower than you would prefer. So the introduction of drift correction in modern TEM digital camera systems has been an effective aid in combating these issues. Each image is automatically realigned with the data collected prior to it, and it produces a sharp, clear result for you. Now, this feature has been made possible. This feature has made it possible, to an extent at least, to ignore sample drift during the acquisition of an image, and it allows you to increase the magnification and or resolution of that ultimate image. So while this technique allows for a small amount of lateral image movement to be kind of erased from the final photo or movie clip, it only works in the X and Y plane. Changes in the Z plane, which affect focus, cannot be addressed in this way. A further problem is that this is only effective under limited circumstances, where your field of view is, the field of view you chose is larger and the rate of drift has to be low. As the sample misalignment is removed from each image, significant portions of the field of view can be lost as the corrections are applied because the digital pixels are overwritten with incoherent information. So depending on the magnification you've chosen and the rate of drift, you may have little or no time to capture your image before the area of interest is cut off or lost. So obviously these algorithms can't account for any real abrupt change in the image shape. So in a real in situ experiment that causes a specimen to react or morph in a significant way would probably fool this type of simple image correction scheme. So the camera corrections alone cannot break through this barrier for real world in situ experiments that take extended periods of time. So I think before we have a valuable conversation on drift, we should consider the many sources of it in typical TEM work. A new TEM today has a fundamental resolution specification that's deliverable if the drift at the time of data acquisition does not exceed a level of around 0.5 nanometers per minute. And I show that here in the dotted orange baseline on this graph. When working above this level, there's going to be some compromise or corrections that may be required to maximize captured data quality. And there's many sources that can contribute to an increased level of drift. I'm sure most of you are familiar. Some are subtle, some such as thermal changes in the lab environment. Some are more experiment dependent, especially when using the system in a certain way or when changing conditions dramatically. Holder insertion, mode changes, and other operations may require some delay until the drift settles back to a level stable enough for high resolution work. In situ experiments can contribute an inordinately large amount of drift, since they are pretty much by design meant to induce chaos by the application of aggressive stimuli on your samples. And the resultant movement and changes in size and shape, it can be daunting to manage. So, as mentioned on the last slide, the explosion in situ TEM brought new sources of drift to be dealt with. The reactions that are triggered can lead to very fast dynamics. And you've got particles traveling on a substrate, joule heating caused by high current during electrical failure tests, rapid growth of large structures at high magnification. And all these make the situation much more challenging. In certain applications and situations, these conditions may completely eliminate the ability to reach high resolutions and will rob you of enjoying the full capabilities of your TEM. So as an example, the crystallization of a silver nickel phosphide particle was made famous in our last AXON webinar, and it had a significantly higher average drift rate as we ramped the temperature during the experiment, and our experiment took approximately 10 minutes. And you can see the average level of drift in this situation was almost 2 orders of magnitude higher than the TEM baseline specification as shown here. So let's take a look at what trying to manage that particle reaction without AXON might be like. Here is an image of that silver nickel phosphide particle. So the optimum field of view chosen at this high magnification captures the entire image. This is a 20 nanometer width image, so the particle itself, which is approximately 15 nanometers wide, doesn't have a lot of room for movement within this area. This area within the green boundary is the region of interest that I want to capture throughout my 10-minute heating crystallization experiment. If the induced drift I mentioned is occurring in this direction, it means I only have approximately 3.5 nanometers of travel before I start to crop off part of my region of interest, or my ROI. As the sample drifts, my ROI shifts closer and closer to the border of the field of view until it begins to be cropped off the page, and my attempt at capturing this data is over. Capturing an image at this magnification and rate of drift, it's not easy for anybody. You'd have to be incredibly skilled and patient, and you have to make dozens of complex operations every few seconds at inhumanly fast paces in order to try and reproduce our results. Now, these corrections that you'd have to make are a combination of electron optical beam shift and mechanical stage movements at various points throughout the experiment. And this will include also resetting certain conditions and possibly refocusing the image also throughout the experiment. AXON automates this entire process by handling all of these corrections in the background while we enjoy watching the particles transformation without effort. Despite the severe rate of drift, which is far outside the capability of any digital camera or software image correction product, we can watch this reaction and map the path that this particle actually traversed in three-dimensional space. So we've talked about AXON and the superior level of power it has to eliminate the drift in your TEM work. But how much is too much for AXON? So the experiment data you see is based on rate of actual drift as captured in an experiment using our double tilt MEMS-based heating system called Fusion Select, where we used a gold on iron oxide sample. In the context of this particular study, the rate of drift was centered approximately around 15 nanometers per minute, in that range on average during the heating ramp. Note that all drift numbers reported today from active heat are all the drift numbers reported today are from active heating ramps. This is not after any settle time. This is during the action, because no settle time is actually needed anymore. The silver nickel phosphide particle experiment we just used to illustrate the difference between the AXON performance and that of image correction features found in TEM operating systems and digital TEM cameras. This particle runs at a much higher level, shown here at around 35 nanometers per minute. Now, this last data set corresponds to an experiment that was collected by AXON that we ran for a previous webinar. This time we were using a very popular bulk furnace heating holder. Now, while this heating holder is found in labs around the world, it's well known that it is seldom used to attempt any sort of elevated temperature work at high magnifications. It has a much larger amount of drift, and it averaging above 100 nanometers per minute easily during a majority of the 10-minute experiment, as shown on this graph. Now, this is the ultra-high magnification image from that bulk furnace heating holder. It's atomic resolution imaging of that entire 10-minute collection. Now, despite the drift I just showed you, AXON has no problem making this stainless steel sample behave at temperatures at which it typically would be most unstable. So this example will breathe new life into an expensive holder system that customers have likely given up on, assuming they would never be able to use it at high resolution. So jumping back even earlier, I explained that the data in this webinar was meant to illustrate to you the impact that AXON will have on your work. And that means we want to clearly identify the specific improvements made only by the addition of the AXON system. Now, this is best accomplished by the use of a controlled experiment, and luckily we have lots of those. So just like so many other manufacturers of scientific instruments, we have a regular need to demonstrate the capabilities for customers who are investigating them for purchase, or perhaps to train current customers on expert use of their new in-situ systems. And we chose one of these experiments since we know their behavior. We know when and where they will respond to the stimuli, what's the best data we would expect in the end, and perhaps most importantly, we know that they present us with no surprises. So I know this sounds rather boring, but if we're going to do this in this way, we will have established that controlled experiment we need for our example today, and it will leave AXON as the only variable in the experiment. So whatever difference you should see in the results, it was from the addition of AXON alone. Would this prove our theory? Would the experiments be far faster and easier to run? Would the data be far better? Would all the embedded metadata allow us to generate anything meaningful, any meaningful visualizations, meaningful analytical conclusions? And most of all, would this AXON system enable an experiment that we run hundreds of times to produce something that we've never seen before? Maybe perhaps something that's even scientifically relevant. So we'll show you these results here in just a moment. So as I mentioned just in the last slide, we chose an experiment that Protochips applications engineers have performed regularly over the past years. It's a gold on iron oxide particle that reacts with the addition of heat. It melts, it coalesces, it edges a carbon substrate at different areas in the heating ramp. Yeah, and honestly, it's really not that interesting of a reaction, but we know what to expect every step of the way. and also what the best data looks like. So it's a perfect controlled experiment for this exercise. So first, the sample has to be inserted into the TEM. The operator has to make alignments that are necessary and find a good area of the specimen for us. And then next we can acquire a first batch of images and maybe some spectroscopy. So we've got an initial pre-experiment data set. Now, in order to make this a fair apples to apples comparison, we're going to assume that we haven't run this sample before. So we don't take any shortcuts that could spoil the results. Therefore, we're going to pretend we don't know where it reacts. We need to drive through a large range of temperature until we find those trigger points where things start to get interesting. And we won't capture images here typically since we're focusing on ramping temperature, and chances are we'll be forced to stay at lower magnifications, and we'll be preoccupied by, following the sample and trying to maintain it in the field of view. Now, once we get to the reaction points, we ramp as slowly as necessary to minimize the drift and enable reasonably high magnification image capture at some of these more stable points. Now, as you can see, these points of image capture are not possible everywhere, especially for reasons we explained earlier in the session. Also, the magnification setting for this image acquisition is also probably lower than we would have liked. Now, at the end of the temperature changes, we can hold the temperature at a constant level and capture the best images possible once things settle down. So now that data has been captured, we need to organize and label it with the parameters of the experiment, which is what we're dreading. In this case, the only real attribute available is temperature, but it's still a tedious manual exercise to align this against the experiment timeline. And even after much time and effort, the results of the level of accuracy is somewhat questionable. And finally, a review of the publishable images, that can inspire us for further experimentation or techniques to expand our knowledge of the process. So since there's 3 parts in this experiment, which are virtually the same when we used AXON and when we did not use AXON, we're going to remove them to let only those portions remain that are available for enhancement. Therefore, we'll remove loading and finding our initial image area at the beginning, the post-mortem steps, and finally, we'll take out the data review and planning section at the end. So let's combine these remaining sections of our experiment. In order for this comparison to be valid, we need to run the pre-AXON simulation in such a way that illustrates what a researcher might do in order to generate the best data we suspect is possible. Now, since we're still under the assumption that we've never before run this experiment and that we had never seen this sample react before, we can't technically yet know at which temperature things would start to change or how aggressively we could ramp the temperature. So with that in mind, we realized the best path to success is an experiment like this might be to split it into 2 sections, a preliminary investigation to gain some experience with the sample, and a final data capture session for the best data collection once we had gained confidence. So these are the separate experiment runs. We'll label them day 1 and day 2. To begin the day 1 work, we would perform a slow preliminary heat ramp over the fusion select temperature range, and we'd identify the key moments of any reactions. We would need to be carefully documenting everything along the way that we noticed in order to capture even subtle reactions in behavior, and we'd capture pieces of images along the way as possible. This will take time. Once any reactions are witnessed, it becomes possible then to plan the next experiment and target specific moments that may have been missed or could have been recorded could not have been recorded at the proper magnification. Now on day 2, we'd begin with a much higher level of confidence and experience with the sample. So we'll go ahead and ramp much more quickly in the first stage to get just below the trigger temperature, and then we'll slow down through those reaction points, hoping to minimize any instability in the sample and maintain as high a magnification as possible without losing track of the region of interest. Now, marrying the information on temperature or any other experiment parameters with the captured images will now be a real tedious exercise with limited results, but it needs to be done. It needs to be done before we can draw any conclusions that are presentable. And those of you in the audience today who have had to perform this data alignment know that this one step alone can sometimes take as long or longer than the experiment itself. So now I want to touch on one of the first enhancements that really struck us in this experience, and it was the time it took to finish our experiment. If we combine these last two pieces to form the full experiment, it gives us an end-to-end time of approximately 13 hours. Again, this is what we should expect these tasks to take if we want to reliably have a chance to produce the best data possible in a world without AXON. Now, since we already knew what the best data from this sample looked like before we started, we know that a more casual or less stringent approach easily could have caused us to fall short in our ultimate results. The complete experiment, performed for the very first time using the new AXON system, took only just over 3 hours. It was a mere quarter of the time of the non-AXON timeline. And even though we still have an experiment step remaining to review and make decisions on our data, the AXON notebook application makes it possible to perform that work. And we can do it during live data collection. So we can legitimately absorb this step within the 3-hour data collection run, which would save us even more time. The first time we did the experiment with AXON, we captured everything we were looking for and more in those 3 hours. There was a large amount of new information we learned from that one experiment, and you can see we have it listed here in these bullets. And it's not a short list. And a couple of these we only first noticed during live review sessions if we didn't see it happening in real time. Because we're constantly recording everything along the way, you can really focus on the live response, but you know your data is being saved for your later review. So I really want to take a deeper dive into this live review that I just mentioned, because it was a critical feature that was a huge time saver for us. The live review was done with the AXON notebook application, and it gave us a level of visibility and clarity into the experiment that helped us make faster and smarter decisions. The notebook app is a free software application that comes with AXON, and it enables data review, metadata overlay, and data export on demand. We could review hours worth of data while we were still at the TEM and the experiment was still running and recording. And we could also quickly collaborate with other stakeholders since the notebook app can be downloaded on any computer, and we'd get their feedback even before the session ended. So we would take this information and we were able to make thoughtful decisions on what our next steps should be. The biggest one being, did we already have what we needed? If not, we would be able to book our next TEM session quickly because the TEMs book up fast. Now, if so, we would actually be able to leave early and save some TEM time even. Should a specific set of parameters be revisited? Should a new area of the sample become the focus? Both of these were much easier to answer during the review of the session because some dynamics were either exceptionally slow or others were exceptionally fast. And sometimes it was difficult to assess the situation in real time. In the review session, we could speed up and we could slow down as needed to ensure we fully understood what we were seeing. Should a new sample be prepared? We always wanted to know this as soon as possible. Sooner rather than later was always better. Let me just show you how easy and fast it was to review the data live with the notebook app. So when you're ready, you just click the review session button on the left and the AXON notebook app will open up in a new window. Once it's open, all the data that's sitting in the buffer will automatically load. At the bottom of the screen is a scrubbing bar where you can use your mouse to drag the cursor back and forth and flip through the images as if they were a movie. And we could scroll quickly, we could scroll slowly, we could go over and over again in the same spot, and we would really gain an understanding of what was going on. On the right, there is an array of parameters that can be overlaid onto your images for export. But we'll go into this particular detail a little bit later. So to summarize what you're seeing here, we were reviewing the entire TEM session instantly. It's hours worth of data, and it was while AXON was still recording in the background. Being able to access this kind of information as needed and so quickly really enabled us to be much more efficient with our time. So the next enhancement of this experience that really stood out to us was that we had better final data. So what does that mean, you ask me? Let me tell you. So prior to introducing AXON, our quote final data, which for us in our case this would be used for marketing material. In your case, it's likely the images you're choosing for publication. Was typically captured in one of two different scenarios, either during highly dynamic times and or during temperature ramps, where we would sacrifice resolution to be able to capture the action, as you can see in the upper example here. Or after all the chaos has settled and desired temperatures have been reached, where we could then acquire images at a much higher resolution, as shown in the lower example here. Now, essentially, we stuck to these two scenario options because it's difficult to capture both highly dynamic instances at ultra high resolutions we preferred, because it was the TEM operator would usually struggle to keep the desired region of interest in the field of view. Now, the sample movements and the drift they can be unpredictable. So unless clairvoyant, even the most experienced TEM operators would struggle in a high resolution, highly dynamic scenario, and it's due to no fault of their own. So with AXON, we found that the automated stabilization actually allowed us to marry both scenarios. So now we can capture highly dynamic events at ultra high resolution. We can record the entire experiment, temperature ramps and dynamics alike, at high resolutions because we're no longer limited by how fast our brain can process what needs to be adjusted with the TEM. So this leads to an entire reel of data that's captured during the most exciting areas of the experiment. And every image in that reel can qualify as the final data. Here on the right are two separate snapshots pulled from this center video and zoomed in, and they were taken during very dynamic times of the experiment that would have been very time intensive and difficult to capture before. So the next area I want to touch on as far as our experience in this experiment was a huge enhancement in how rich our data was in information. So again, the AXON Notebook app really was a superstar in our experience. The data can be exported with overlays already inserted, generating either presentation ready, publication ready, or in our case, marketing ready images with no effort. So to add overlays, you just click the review session button on the left-hand side of the AXON screen again, and again, the Notebook app will pop up in a separate window. All the parameters available are shown on the right-hand side, and we just simply checked the ones we wanted to display on our images, and that was it. Once the overlays were chosen, we could use that scrub bar again to scroll through the data and see the overlay change with the image. The drift corrected and overlaid data can then be exported as lossless PNGs, ready for insertion into a talk or a publication. Now, we aren't publishing this data from our experiment, but again, I mentioned this earlier, I think most, if not all of you, have experienced just how tedious it is to process and overlay information onto your images. Here, it's just the click of a button. And a newly added feature allows you to now tag the series of images you find most interesting, and then you can just discard the rest on the spot. You'll end your session with only the data you want, a lot of free hard drive space, and a significant amount of free time because you completed most of your post-processing in real time. Now, while the images alone can be very interesting and insightful, I think we can all agree the ultimate goal of most experiments is to quantify in some way an unknown phenomenon and come up with actionable next steps to further the research. AXON makes quantifying these results much less tedious than before. We had no paper notebooks in the lab with us because we knew everything was being aligned in the background, so we didn't have to worry about keeping track. And it's not just the temperature and the time either. You can see here there is a large array of data from the Protochips in-situ systems, the TEM, and the imaging detectors that's automatically embedded into each image, including many, like these shown here, that are used in calculating electron dose. Now, all the recorded parameters you see here are compiled into an Excel sheet where we could then use that to create graphs and trend charts that align with the images. Now here, pay careful attention to the chart in the upper left portion of this screen where we're plotting time versus temperature. The green cursor that tracks along to indicate the temperature is also being modulated in size to illustrate the corresponding level of drift at that moment. I know this sounds very difficult, but the way AXON packages the data for you, things like this are easy. And this is just one example to inspire you because these types of correlations are incredibly powerful ways to tell a story in a publication. Now, one of the most surprising things from this whole experience was what was revealed to us in the experiment that we had never seen before. So for instance, this graph maps out the drift of this gold on iron oxide experiment we've been talking about. And it illustrates that most of the time it stays on average in that 15 to 20 nanometer range. Now there's a moment here at 1123 degrees Celsius in which the drift rockets up past 100 nanometers per minute and before returning back to the more stable baseline level. So this is a really good example of a real world in situ experience because these unexpected actions come from the aggressive application of stimuli. Now, in this case, the gold particle we were watching was connected to support in a cantilevered fashion. The raw video data here has only been corrected by the AXON beam shift repositioning. So AXON is performing some action here, but it hasn't met the digital correction yet. So you can't see exactly how far it's trying to travel in this experiment, but we can see clearly that while heating rapidly, the gold particle starts to form a graphite shell, which begins to merge with a larger graphite structure. And at some point, they are only attached by a fragment of material, and the gold particle starts to move erratically, explaining this spike in drift. Now, in addition, there's a structure on the bottom that suddenly moves on top of the graphite. But AXON simply doesn't care. AXON doesn't care, and it effortlessly manages your experience so the images continue to be collected smoothly and capturing all the action for your review. The finished AXON data, as seen here after the digital correction, is perfect. And so here, the sample in this instance causes the reaction at this stage causes the particles in our selected region of interest to travel thousands of nanometers in three-dimensional space. And AXON allows us to track while maintaining our target area throughout this work. And it's as though any of the movement and drift wasn't happening at all. So there were several examples from this 3.5-hour experiment with the gold on iron oxide that we showed throughout this webinar, where we ended up classifying the results as, quote, previously unattainable or as invisible data. And this is because this is data that would have been impossible to capture prior to AXON because there's just so much unpredictable activity that makes it difficult to maintain a region of interest within a small field of view. In fact, we never saw any of this prior to AXON. So here are some of our favorite examples. Here, AXON went beyond what is humanly possible and held the region of interest in the field of view at atomic resolution throughout several chaotic events. There's a temperature ramp, the nanoparticle travel over the support, carbon etching by the nanoparticle, and sublimation of the iron oxide flake. Here, AXON captured the dynamic formation of the graphite shell around the gold nanoparticle during a high temperature heating ramp. And through this, it maintained really impressive atomic resolution. And if we zoom into this corner here, we were able to observe atom by atom growth of a single graphite layer in the middle of a temperature ramp from 1100 to 1200 degrees Celsius, in the middle of the temperature ramp. Constant, the reason we were able to capture this was constant stabilization by AXON. It made every single frame usable from the TEM session. And then we also have the constant recording, which allowed us to capture this in the first place because we were not expecting this, nor were we looking for it. AXON is about improving your quality of life during your TEM experiments. You're increasing productivity, opening up the previously unattainable side of your experiments, and all while making the workflows simpler. So we hope you'll take advantage of this new normal to establish a higher level of routine performance in your lab. AXON was designed to improve most everything you do with your TEM, even if that never involves a MEMS holder. AXON wasn't designed to address any particular product issue. It was developed to address the steep learning curve associated with achieving high quality TEM results by eliminating many of the hurdles. The new freedom you have with the workflow automation and system optimization from AXON will let you conduct your science with a new speed, and it will propel your work and help make up for lost time in the past and accelerate all your future work. AXON sets up a springboard from which so many things now become possible. The machine vision platform it establishes presents the opportunity for us to deliver more and more software solution modules that will continue to boost you over those hurdles that tend to slow you down. So we have reached the end of the presentation. Thank you so much for joining us today. I hope you learned something. I hope you feel inspired. I hope you're excited to kind of get back to work and generate, generate some new publications, some high impactful work, and we hope AXON will be a part of that. So we've got some time left over, and I'd like to pass the mic over to our Senior Director of Global Applications and Marketing, Mike Coy, to handle and modulate the question and answer session.
Great, thanks, Jen. Great job.
Thank you.
I've enlisted a couple key people to help us with questions. So joining me to field some of these questions is Dr. David Nakashi, not only the CEO of Protochips, but also the product manager for AXON. He'll be wearing both hats for us today. And Joe Sanguidolci, he's our Executive Vice President of Global Sales, Marketing, and Service. So welcome, guys, and thanks for helping us out. Let me take a look at the questions we've got set up here. And Jen, I think this first one is actually probably best suited for you. What happens if I want to move to a different location while AXON is running?
Oh, sure. So AXON is not meant to completely take over and lock you as the operator out of the experience and out of your experiment. AXON is meant to facilitate and work alongside you. So there's definitely instances where you may actually be able to sit there hands off while AXON is controlling all of the stabilization for you. However, if you decide you want to move areas or you want to actually adjust the focus because you're more interested in a different area of the particle, that's no problem. You can go in and adjust as you please, and AXON will let you take what you need, take the time that you need, and as soon as you let go, it will jump back in and help you pick up where you want to leave off, and it'll continue to do those background motions for you so you don't have to think about it. So it's a seamless, it's supposed to be a seamless pairing, you and AXON working together to get better results than you have, than you would have anticipated.
Oh, great. Thanks, Jen. Just a quick reminder before I hit the next question. If you are interested in winning the AXON system, remember that you've got to hang through to the end. There will be a survey that pops up when we finish this Q&A, and Your participation is required for a chance to win. David, I think this next question is probably best suited for you. I heard that dose was mentioned in the presentation. Can AXON actually measure dose?
Hey, Mike, I appreciate it. Thanks for, first of all, I want to also say thanks to all of you for attending here at a time where we can't travel. Many of you, I think, would have expected to see me by now and visited a conference or some type of a just a regular site visit, but we can't do that today. We can't do that during these conditions. So it's nice to be able to get in front of each one of you, even if it's in a webinar capacity. So yeah, dose. Everybody, not only in situ microscopy, but electron microscopy in general, they're obviously very interested in dose control, dose measurements, and certainly dose calculations. This actually was a pretty big topic of discussion, if I remember or was told correctly, at the Gordon conference for liquid microscopy. Madeline Dukes, our application specialist in the liquid field for Protochips, was there and relayed some of this information back, and we certainly understand and know why. AXON doesn't actively measure dose, at least not now, but in its current form, if you take the data from your microscope or your camera, in other words, the screen current, the camera conversion efficiency, and you combine that with the metadata within AXON as it is today, time, magnification, spot size, aperture settings, you can take the calibrated data you have combined with the metadata that we have in AXON and much more easily do those calculations even on an image by image basis. And so you may have seen in this webinar or even a previous, we posted a short video on YouTube some weeks ago called the AXON Experience. If any of you haven't seen it, I suggest you look at it. It sort of in 6 minutes takes you through an entire session where you can see the windows and screens and a workflow on how to use it. And you'll notice there's an Excel sheet that's a culmination, or I guess I should say, maybe all of the metadata correlated and spit out in an Excel sheet. So it's not only in the images themselves, but in that sheet. And by adding some of this other information that you would have from a previous calibration into that sheet, calculating dose definitely becomes a much easier accomplishment for you.
All right, thank you, David. Don't take off your product manager hat. I think this question is probably best suited for you as well. In one of your heating videos, AXON seemed to follow a particle as it was moving on the carbon. How does the user decide what the drift correction operates on?
Okay, that's a great question, and maybe it's worth pointing out when you're looking at data like this, there's two things happening. There's the natural drift from changing a temperature, but then whatever it is you're looking at might actually have some motion in and of itself, whether it's simply maybe a centering particle, it's going through some reaction, maybe the beam is interfering with it in some way. So the way that works in the very beginning is you simply have a region of interest box and you draw that around the area that you're wanting to use your cross correlation methods on. Within that box, there's also a focus box to determine where we want to lock in on focus. And at that point, it's going to do the best that it can through all the parameters that Jen explained to track the particle. So it's just trying to keep the particle within that field of view, and it's trying to keep it as still as possible. So whether it's moving because of a reaction or moving because of a thermal drift or both, it will continue to follow it as you saw in that video.
Okay, and our next question, David, I think ties directly into that. Does AXON have any parameters that allow tuning or adjustments to the way that it controls the drift, or do you just turn it on?
Yeah, very, very good question. And again, I would encourage people to look at that 6-minute video on YouTube called the AXON Experience video. So the short answer to that is there's a lot of flexibility in tuning parameters. I think many people were concerned that it was just a push button operation. And believe me, we tried to make it that way. We're not trying to make this product overly complicated. However, we also realize that many people in the field would like to have the ability to tune and set certain parameters that are important to them to tweak and get the performance just right. And so we've actually opened up a number of those things to let the users make adjustments to, like, for example, how far something might move within the field of view before you end up making a mechanical correction. Think of it like your air conditioning unit. You wouldn't want it to cycle on and off every 1/10 of a degree of change. you want to allow the temperature to drift some bit before the compressor comes back on. Similar to this, before making a physical correction, a certain amount of movement needs to go, and to make it look perfect, that's where the digital aspect of this comes in. So parameters like that are available to be adjusted. For focus, for example, there's some algorithms that can be selected as well for the user, and even down to session management, file locations, what information is saved, raw, corrected, non-corrected, all of them. All of those things are adjustable. There's a wide variety of parameters, and I think some of that showed in that video I mentioned.
Okay, great, David. I think we're just going to keep your streak going right now. So, here's a question we got a couple times. Is there a maximum level of drift that AXON can manage?
Yeah, that's a great question as well. It's probably the most common question that comes up. And so maybe the best way to describe it, so there's two factors when you think about drift. The field of view, I won't say magnification, but let's call it the field of view. How narrow or wide is the field of view? And then the update rate. And what I mean is, how fast are we getting images, whether it's in TEM or STEM mode. And TEM mode, you would expect most likely a faster rate than STEM mode. So those are the two key factors. So as an example, if you have about 100 nanometer field of view on one axis and an update rate of about a tenth of a second or 100 milliseconds, we can correct for almost 20 nanometers per second of drift. And as you could imagine, the slower the update rate, the less drift you compensate for. The narrower the field of view, also, the lower the drift rate you compensate for, and vice versa in the other direction. So, however, from those numbers, and like I described, it actually can compensate for a very wide range of drift. I mean, in some cases, even over 100 nanometers per second, if those conditions are right. And those update rates really do have to do with a couple of things. They're not just the speed at which the images can be picked off the other computers we're networked to, but it's also a user setting, right? For example, in STEM mode, a user may, for a certain signal to noise, be interested in a dwell time or an update rate that's slower, maybe a second or a second and a half. That nanoparticle result that was shown in this video, for example, just as a point of reference, I think was about 1.4 seconds per image. So that kind of gives you an idea of what it was able to compensate for that rate.
Okay, excellent. Joe, I think this question might actually be for you. We'll give David a break. The notebook utility looks very interesting, but how does it compare to my camera's look back feature?
I know why why you think that might look like something I should answer. I have a little experience with, as do you, with that particular industry term. So look back is a commonly used phrase that refers to one of the more popular cameras in the industry, more the camera lines. And when they have an in situ camera situation, they allow you to have a cache that's running and storing a lot of data. And you can decide how far back in time you want to look back. You can say, I want a second or as much as 20 seconds. And so you'll be able to have your experiment unfolding in front of you and without having to save anything, because again, these cameras, newer cameras today save a lot of data, and they do so very quickly. And if you tried to save every single frame that was being delivered by that camera, you can fill some very impressively large arrays of drive space in some pretty depressingly short periods of time. So you want to be judicious about what you capture. And so the look back feature gives you the idea of the ability to see something happening and to question in your mind, hey, if I had been recording at this moment, would I be happy? And if the answer is yes, or even if it's maybe, you can say, go get that, and it will go back in time, kind of like your digital video recorder or TiVo capability on video players. It'll go back in time, and it will go to the beginning of that reaction in this case, perhaps, and then you can record as much as you like and then stop. So you have essentially captured only the good stuff, and you haven't been recording along the way, filling up drive space just in case something happened. And the way that's fundamentally different from AXON is AXON it really doesn't care, to use a phrase that Jen used in the webinar. Axon's constantly managing a massive amount of data for you. So you could literally be hours into your session and go back to the very beginning or any other portion of it and look at, analyze, decide whether you like it or not, and then tag images or sections of data as stuff you want to keep or stuff you want to get rid of, and you can have this thing kind of clean itself up along the way. But in any case, you can have hours in a session that has not really been recorded yet. It's still in a buffered state. And then after the close of that session, you can decide exactly which pieces you want to export and save into real drive space, the valuable stuff. And that's the stuff you're going to want to save so that you can publish and create movies and high resolution data from. But unlike these other, like the look back feature that was asked about, you really don't have to make little fragments of time, the things you save, and you can make those decisions minutes, hours, days after you've had the reactions happen. You don't have to call the ball within 20 seconds. You have all day long, as much time as you need to make decisions on your data, because it's really managed in a much more efficient way over a long period of time. That's the short answer. There are fundamental differences if you are someone on the fringe of extreme temporal resolution in situ microscopy. But for the overwhelming majority of people who are doing in situ work or general TEM work that would be greatly enhanced by Axon, the Axon solution is a far more flexible and extremely powerful solution.
Great, thanks, Joe. We're starting to get a little bit low on time here, so I'm going to combine a good group of questions that we've got. And David, I'm going to kind of pitch it to you with, what's next for Axon? What should we expect to see? We have a whole bunch of questions that are kind of along that line. So I thought I'd give you kind of an open-ended question to tell us what's coming.
Okay, yeah, thanks, Mike. I appreciate it. I was actually hoping to get that comment and also here at the very end. I know there were a lot of questions that came in during the webinar, and I know you intend to get back to everybody in time afterwards. But these types of questions, what's next? We make the point of saying this is a module-based software, and we talk about synchronicity in particular in that name. So in a nutshell, as you can tell, it's a module-based architecture because we intend to build on this. So this is the fun part. Synchronicity is the first step. It's a foundation. It's creating a set of stable images with time synchronized metadata, right? Especially from our world in situ, time and temperature and pressures and flow rates, as well as microscope and camera data, bringing this all together. You could imagine the power of bringing that in a stack of drift corrected images and time synchronized metadata and handing it to the users to be able to analyze. So that's what we're building on right now. And where we go from here is actually pretty fun. You start thinking about calculated metadata, things that are interesting to us. What can you do to combine some of this data together or draw information out of it that might be buried within it, doing math on some of this data or doing other types of analyses. These are things that can take us into the future. And then finally, providing a way for our users to find correlations in the data itself, the images to the temperature, even things like the mass spec data. For those of you who are familiar with gas cell work in our atmosphere system, we have an integrated mass spec. So we have quite a bit of information that comes out of our system that gives you chemical information, a different kind of chemical information about your reaction. Bringing that back into the stat, potentiostat data as well, if you're doing electrochemistry or battery work. So for us, for our vision, all of us here, our team, our engineers, our entire group, we really look at this as a way to bring it all together into a place that's synchronized with well-behaved images to help our users do analysis on. It's not really our job to draw scientific conclusions. That's on this audience. But what we want to do is everything we can to help correlate and present the data in a way that makes trends and comparisons much easier for you. So with everything, all the data being created today, new detectors, new in situ data, I mentioned mass spec, for example, to higher frame rates and cameras that operate at a higher level of performance. honestly, we feel this is a huge part of the future of microscopy, and we definitely intend to play a pivotal role in helping solve that problem. And I think this is how we intend to do it, is through AXON.
Great, thanks, David. As David mentioned, we've got a lot of other questions, and obviously we're not going to get through them all right now. So we will follow up with each of you, and also please feel free to reach out to your local representative or to Joe or myself. We expect to announce the winner of the AXON system in the coming 2 weeks. We will contact the potential winner by phone to ensure their lab has a compatible system, and to get a few more details and confirm their organization is capable of accepting such a donation. Once we've clarified that, we'll post the news on the Protochips website, so please keep your eyes open. Remember, you do need to answer the survey that's going to pop up in just a minute. And finally, just to close out, we at Protochips want to thank each of you for spending this time with us today. We're very excited about AXON, as I'm sure you can tell, and we're really looking forward to see how AXON can enhance your work and maybe even hosting you and your supercharged applications data at a future AXON event. Thanks, everyone, and have a great day.